Look at the sheer volume of drilling fluid returning from the wellbore. Thousands of gallons of thick mud cascade over the shale shakers every minute. It is easy to look at this fluid and assume the clay suspended inside it is simply bulk mass, passive dirt added to water to make it heavy. If we zoom in past the suspended rock cuttings, down to the sub-microscopic level, these overlapping fanned-out plate structures form a highly dynamic electrochemical engine that dictates exactly how the entire fluid system behaves. To maintain control over macroscopic properties on the rig, like viscosity, yield point, and fluid loss, a mud engineer has to control the microscopic electrochemical state of this clay. Every physical test performed at the surface, from a simple funnel viscosity check to a rheometer reading, is actually measuring these invisible submicroscopic particle interactions. To accurately predict how drilling fluid will react thousands of feet underground, we have to build a working model from the ground up. We will start at the atomic lattice, examine how ions exchange across the surface, and then scale up to the chemical treatments used on the rig floor. True mud engineering relies on manipulating these invisible forces to stabilize massive industrial operations. This diagram illustrates the fundamental atomic architecture of montmorillonite, commonly known as bentonite clay. Notice the three-layer unit structure, a central octahedral alumina layer sandwiched tightly between two tetrahedral silica layers. In a perfect crystalline formation, this silica-alumina-silica sandwich is perfectly balanced. The charges of the atoms cancel each other out, creating a stable, electrically neutral plate. However, natural clay is rarely perfect. During its geological formation, a structural anomaly often occurs within the lattice. Inside the central alumina layer, a single magnesium atom with a 2+ charge occasionally substitutes for an aluminum atom with a 3+ charge. Because a 2+ charge has replaced a 3+ charge, the entire unit layer is left with a missing positive charge. This creates a permanent net negative electrical deficit across the whole clay platelet. To compensate for this deficit, the negatively charged clay plate acts as a magnet. It pulls positive ions, called cations, out of the surrounding environment and adsorbs them onto its exterior surfaces to balance the charge. The total quantity of cations a specific amount of clay can hold is measured as its cation exchange capacity, or CEC. This measurement is the primary indicator of how reactive the clay will be. This permanent electrical imbalance guarantees that the clay will interact forcefully with polar molecules like water, transforming a collection of rigid, dry platelets into a dynamic fluid system. When water is introduced, its polar molecules are immediately attracted to the cations held by the clay. The water molecules drive themselves directly into the spaces between the stacked unit layers. As more water forces its way in, the tightly packed layers separate into individual fanned-out platelets. This physical separation is a process called dispersion. The extent of this dispersion depends entirely on which specific cations are attached to the clay surface. This diagram compares a clay lattice hydrated with sodium ions on the left against one hydrated with calcium ions on the right. You can clearly see a massive disparity in the thickness of the adsorbed water film between the two. The water layer surrounding the sodium bentonite is so thick that the individual platelets spread out up to 4 times as much as the layers in the calcium bentonite. This extreme separation in the sodium clay multiplies both the total surface area and the number of independent particles suspended in the fluid. More surface area means more physical friction between the fluid and the solid particles as they move past one another. On the rig, we measure this internal friction as plastic viscosity. The specific type of cation attached to the clay's surface dictates the total viscosity building potential of the entire mud system. This brings up a critical operational paradox. If monovalent sodium ions cause massive clay swelling, why do mud engineers inject monovalent potassium ions to prevent reactive shales from swelling? This diagram isolates the gap between two clay unit layers. The electrical charge is only half the equation. We have to look at the exact physical dimensions. The space between these layers is exactly 2.8 angstroms. Now consider the physical size of the potassium ion. It has an ionic diameter of 2.66 angstroms. At 2.66 angstroms, a potassium ion nests perfectly within that 2.8 angstrom gap, seating itself deep inside the hexagonal cavities of the silica sheets. This snug physical fit forms a tight mechanical bond, clamping the adjacent unit layers firmly together. With the layers mechanically locked shut by the potassium ions, water molecules are physically blocked from entering the interlayer space, halting hydration and dispersion entirely. Effective shale inhibition relies on using precise physical size to outmaneuver chemical hydration. Once we understand how individual platelets swell, we have to look at how billions of these plates interact with one another while suspended in the mud system. This diagram shows the surface charge map of a dispersed clay platelet. Notice the distinct electrical zones. The large, flat planar surface carries a strong negative charge, while the thin edges carry a positive charge. Because opposites attract, the positive edges of one plate will naturally seek out and link to the negative faces of another plate. This electrostatic attraction is called flocculation. As more plates link edge to face, they build a rigid, three-dimensional matrix throughout the fluid, often described as a brush heap structure. This internal structural matrix directly dictates two key macroscopic measurements on the rig: yield point, which measures the force required to get the mud flowing, and gel strengths, which measure the fluid's ability to suspend cuttings when circulation stops. This behavior contrasts sharply with aggregation. This diagram shows aggregation, where divalent cations, such as calcium from cement or anhydrite, cause the plates to stack face to face. Stacking the plates thickens the individual packets, which reduces the total number of independent particles in the fluid and eventually causes the viscosity to drop. Every rheological change observed at the surface is a direct reflection of these specific association states shifting and reforming in real time. Let's apply this model to a common rig floor scenario: a sudden, detrimental spike in yield point and progressive gel strengths. The fluid is thickening rapidly, indicating severe edge-to-face flocculation. The standard operational response is to inject chemical deflocculants, like sodium acid pyrophosphate or lignosulfonates, into the mud system. This diagram illustrates exactly how these chemicals work. They function as highly powerful anionic, or negatively charged, dispersants. Watch as they enter the matrix and specifically attach to the positive edges of the clay plates. The strong negative charge of the thinner completely neutralizes the positive charge along those thin edges. Without the positive edge attraction, the edge-to-face bonds can no longer hold. The plates repel each other and break apart, physically destroying the flocculated brush heap structure. As a result, the yield point drops, restoring normal fluid flow. However, because the plates remain dispersed rather than aggregated, they continue to lay down a tight, impermeable filter cake against the wellbore wall. This injection physically alters the fluid's structural matrix at the atomic level, restoring flow by dismantling the electrical bonds of the brush heap. A master mud engineer commands macroscopic industrial forces precisely because they understand the microscopic geometry of the atomic lattice.